Okay, I wanted to give you another example of implicit differentiation to help you with your My Math Lab homework that's due Wednesday morning at 10 a.m. Here's an equation, and notice this is different than the types of equations we've been working with so far. So now this is a little different because the x and y are kind of interlocked together. So our goal is to find the rate of change of y with respect to x for this relationship of x and y. In order to explain the steps, I'm going to use this notation for the rate of change, of y with respect to x. But it's kind of a mouthful, and I need to say it over and over again throughout the example. So I'm going to use the terminology y prime, although we've kind of said before that that was like off limits. But needing to say it many times in this example, I think it's okay for us to call it y prime for ease sake, and knowing that what it means is the rate of change of y with respect to x. Every time we see that, that's our image of it. We know that that's rate of change of y with respect to x. And so we know that this there's a curve that represents this, and that curve is made up of every point whose x and y coordinates satisfy this equation. Any point that's not on the curve, the x and y coordinates of that point will not satisfy this equation. The two sides will not be equal. So we want to come up, so even though it's not a function, y is a function of x, it still has a curve, and we can still talk about the rate of change of y with respect to x for points on that curve. So we want to come up with an equation for dy dx, or I'm going to use this, I'm going to use y prime. So y prime, what does y prime equal? Because that's our final goal, so that we can have an equation given the point x and y. That equation will tell us the rate of change, the relationship between x and y, at whatever point x, y you plug in. Okay, so here's how you do that. So we do what's called implicit differentiation, which means we go term by term, and we differentiate term by term. So what we have to keep in mind, though, is when we come to differentiating y, well, we think that we know that y is equal to some equation of x's, even though that would be very difficult to find here, to isolate y. And so, for instance, it might look like this. Okay, so this would represent whatever equation of x's, whatever expression of x's you would have that would equal y and would give you the same curve as this. So when it comes to taking the derivative of any y, really we'll have the chain rule, because we'll have, for instance, this y squared. It will be 2y, but then since y is a function of x, or y is an expression of x's, then you'll have to chain on the derivative of the y. Okay, I hope that makes sense. So anytime, basically, you have to use the chain rule anytime you come to the derivative of a y, because of this reason right here. Okay, so let's just begin here. So here's our first term, 75 sine x minus y. So we're going to differentiate, or take the rate of change with respect to x. So that would be, so what's the overall structure? The overall structure is 75 times sine. So that derivative would be 75 cosine. Okay, we'll leave the interior part the way it is, but then by the chain rule, we have to multiply by the rate of change of the interior. And the rate of change of the interior would be the rate of change of x, which would be 1, minus the rate of change of y, which would also be 1, but by the chain rule, times y prime, or the rate of change of y. Okay, so that whole thing that I've done so far is the rate of change of 75 sine of x minus y. So next we're going to go on to 3y squared x, And so the overall structure of that is a product. We're going to use the product rule. So minus, so we'll start with the derivative of the first times the second. So the derivative of the first is 6y, but by the chain rule we need a y prime. So that's the derivative of the first times the second plus the first times the derivative of the second. Derivative of x is just 1. Okay, so this whole thing right here is the derivative of 75 sine x minus y minus the derivative of 3y squared x, which is a product rule. Okay, coming to the right side, now we have we'll have to take the rate of change of e to the xy. Overall structure is e to the something, and we know that derivative is e to the something. But then, by the chain rule, we'll have to multiply by the rate of change of the interior function. Well, that's x times y, and that is, to take the rate of change of that, will be product rule. So we'll do the derivative of the first, 1, times the second, plus the first, times the derivative of the second, which would be, derivative of y would be 1, by the chain rule, y prime. Okay, and then we take the derivative of this constant, minus 67, should be 0. Okay, so that's our first step. Basically, we had an overall structure of sine, so our rate of change was cosine. We had an overall structure of product rule, of a product, so we did the product rule. And then we had an overall structure of e to the something, so we did e to the something. And then by the chain rule, we're going to chain on product rule, because the interior function was a product. So the rest is basically, again, what did we want? We want to figure out what this equals. So we're going to have several terms here. We're going to expand out the terms, and every term that has a y prime in it, we're going to move to the left side of the equals, and everything that doesn't have a y prime, we're going to move it, keep it on the right side, or move it to the right side. So first of all, we've got to distribute. We've got two terms here, so I'm going to distribute the 75x minus y, first of all, times 1, or sorry, 75 cosine of x minus y, and then minus, again, that 75 cosine of x minus y times 1 y prime. So that's going to be 75 y prime cosine x minus y. Okay, so all I did there was I just distributed this term into the parentheses. That thing times 1, that thing times minus 1 y prime. Okay, and then we'll, let's expand out. All we have to do now is just subtract both of these terms, because we're subtracting that whole sum. So I'll write minus 6y y prime x minus 3y squared. And again, I'm going to distribute the e to the xy to both of these, because it's e to the xy times this sum. It's going to be e to the xy times y plus e to the xy times xy prime. And then the 0 goes away. Okay, so we got all our terms expanded out, and we look for the ones that have a y prime. Those will go to the left of the equal sign. The ones that don't have a y prime will go to the right of the equal sign. So this one is going to head over to the right. This one's going to stay here. So we got minus 75 y prime cosine x minus y. This one's also going to stay. It's got a y prime. So minus 6y y prime x. Okay, And then this one is going to be, since it has a y prime, we want to move it over to the left. So it's plus over here on the right, so we're going to subtract it from both sides. Minus e to the xy, xy. Okay, so I grabbed this one and left it, this one, left it on the left, and this one now I've moved over by subtracting that term from both sides. The remaining terms that don't have a y prime will go to the right of the equals. So the first one's this one, so it'll be minus 75 cosine x minus y. And then this one, moved over, we'll add 3y squared to both sides. And then here this will just stay as it is, so plus e xy. Okay, we're doing good. We've got every term of the 6 terms. We've got the 3 that have a y prime on the left, the 3 that don't on the right. So our whole point in doing this was to isolate y prime. So now I can factor it out on the left-hand side. So I have minus 75 cosine x minus y minus 6yx minus e to the xy x equals, same thing, copy and paste. Nothing changed there. Again, the goal is find what the rate of change is. The rate of change is y prime. So every term that has a y prime, move it to the left, then factor y prime out of those terms. So we are virtually done. All we have to do now is divide both sides by this thing in parentheses. And we get y prime equals. This will be our numerator. Divided by, inside the parentheses here, denominator. All right, so let's. I'm gonna check my work here. Okay, so that right there is our rate of change for this function, and it's a function of x and y. We saw that for a given value of x, there might be more than one point that have the given value of x. So it no longer just depends on x, but a point on the graph, and therefore the rate of change at that point depend on an x and a y. And so we see that in the rate of change equation, that you'll need the full ordered pair, not just x, to compute